Hello children, welcome. This is JEE Crash Course, and in today's session we are discussing numerical problems based on system of particles, rotational motion and gravitation. We have already discussed the synopsis. We are familiar with the basic concepts. Now it's the time to take up a couple of problems to use those equations. Example 1. Two light vertical springs with spring constants K1 and K2 and same natural length are separated by a distance L. Their upper ends are fixed to the ceiling and their lower ends to the ends A and B of a light horizontal rod AB. A vertical downward force F is applied at the point C on the rod. AB will remain horizontal in equilibrium if the distance AC is okay. So let me show the construction. This is here and you got another spring here and this is a rod. The rod is of length L. Actually this part is of length L. Now at C a force F is applied. The spring constants are K1 and K2. The question is, what is this distance AC? Assume this distance to be x. So clearly this will be L minus x. Now also assume that in this case x naught is the elongation of each spring. Because the same force is applied, we will assume that the system remains horizontal. So x naught is the elongation of this spring. If x naught is the elongation of this spring, then let us consider the torque. Torque about C, this particular point. So what are all the forces about this? Force F is here and K1 x naught is here, K2 x naught is here, and we have mg acting at the center, right? So now if I consider this one, this is a light rod, so clearly this part does not come into picture, right? And thus the torque about this particular point C due to this force, which is K1 x naught into x, should be equal to torque due to the other K2 x naught into L minus x. And if you simplify, you get x is equal to L into K2 divided by K1 plus K2. So the value of x which satisfies this requirement is L into K2 divided by K1 plus K2. So what is our correct choice? L into K2 divided by K1 plus K2. Example 2. A uniform disk of mass m and radius r is released from the position shown. PQ is a string, OP is a horizontal line, O is the center of the disk and the distance OP is r by 2. The tension in the string just after the disk is released will be okay. So the arrangement is of this kind. This is the construction. So this is r and this is r by 2. Okay. Now if you consider this arrangement, let us draw the free body diagram. If you draw the free body diagram, what are all the forces? Mg is down, T is up, the tension is in this direction. So now let us apply Newton's second law of motion at O. So what are all the forces? Mg minus T, that should be equal to Ma, as the system is not in equilibrium. And we also have torque is equal to I alpha about the center of mass. Therefore, what should we write? What is this torque? The torque is provided by T about this particular point. So T into R by 2 is equal to mr square divided by 2 disk. So its moment of inertia is mr square by 2 alpha. And we also know that A is equal to R alpha. In this case, it becomes R by 2 alpha. So if I substitute all these equations into say 1, what do I get? mg minus T is equal to m into A. A is R by 2 into alpha, right? A is equal to R by 2 into alpha. And I can find out the value of alpha from this equation. So let me substitute there. So what do you have? mg minus T is equal to, what is it? M into alpha is already written. Alpha is nothing but A is nothing but R alpha, that is R by 2 into alpha. Alpha is T into R by 2 whole divided by mr square divided by 2. So now T is an unknown. You can simplify this for unknown and you will end up with T is equal to. I want you to simplify this one. I am writing the final answer here, 2 mg divided by 3. So the tension in the string is 2 mg divided by 3. Example 3. A uniform ladder of length 5 meter is placed against the wall as shown in the figure. If the coefficient of friction mu is same for both the walls, what is the minimum value of mu for it not to slip? Okay. So here is the construction. This is 3 meter, this is 4 and this is 5. So if you show all the forces, what are all the forces? At end A and at end B. At end A, normal reaction N1 and friction which acts along this direction because the tendency is to slip in this direction, so friction acts backward. And at B, normal reaction along this direction because it's resting against the wall and the tendency is to slip in the downward direction, therefore the force of friction F2 acts along this direction. And at its center of mass, the other force is mg. So these are all the forces acting here. Now let us consider the horizontal and vertical equilibrium. Suppose I consider horizontal. Along horizontal, what are all the forces? The forces are F1 and N2, correct? F1 and N2. So if we consider these forces, we will write the equations. Horizontal, F1 should be equal to N2. F1 should be equal to N2. Is it correct? Yes, the only horizontal force is this much. And let us consider along vertical direction. Along vertical direction, what are all the forces? We have N1 plus F2 is equal to mg. N1 plus F2 is equal to mg. And what is this F1 by the way? F1 is nothing but mu N1 and F2 is equal to mu N2. F2 is equal to mu N2. So we can substitute for these details in the equation and we can get the value of N1 and N2, right? So now the question is, what is the question? The question is about finding the value of mu such that it does not slip. So with the help of this, as I said, N1 and N2 can be obtained. Now we need to consider the rotational equilibrium. So now let us consider the torque about say A or B, maybe A, B. So torque about B is equal to 0. What is that torque? So we will write it about this point, F1 into 4. So F1 is acting here and 4 is the perpendicular distance between them, plus mg into This is the direction of mg and I want the perpendicular distance between this point and this point. So what is that equal to? 5 by 2 into cos 53 degree. This is 3, this is 4, so this is going to be 37 and this is 53. So we have mg into 5 by 2 into cos 53. That should be equal to, what is that? So that should be equal to N2 and F2 do not produce anything. So about this point, N1 is producing the torque, mg is producing the torque, these two do not produce any torque. So if you simplify this, this turns out to be how much? 0. That's right. Because F2 and N2 pass through that point, the only two forces are mg, F1 and of course N1 is there, I'm sorry. So this must be equal to, because N1 is tending to produce the rotation in this direction and mg tends to produce the rotation in this direction and F1 also tends to produce in this direction. So what is that? N1 into 3. N1 into 3. So we can simplify it further. We get 4 mu N1 plus 3 mg divided by 2 is equal to 3 N1. I simplified this one here and that gives us how much? 3 mg by 2 is equal to 3 minus 4 into mu N1. 3 mg by 2 is equal to 3 minus 4 mu, that is 4 mu into N1 is mg divided by 1 plus mu square. So now we have mg and mg cancelling and we have a quadratic in mu. So what do we have here? 3 by 2 is equal to 3 minus 4 mu 1 plus mu square. Or we can simplify this quadratic equation, and I am just taking you not through this simplification, I am writing the end answer. Mu turns out to be 1 divided by 3. So coefficient of friction required for it to be in equilibrium is mu is equal to 1 by 3. It's simple. Once again I repeat, this is just a question based on the equilibrium, so you can consider the torque about this point or torque about this point, about any point. In fact, there is no rotation, so I can consider the torque about any point. The net torque turns out to be 0. Next one. In a gravity-free space, a disk of mass m0 rotates freely about a fixed horizontal axis through its center. A thin cotton pad is fixed to its rim, which can absorb water. The mass of water dripping onto the pad is mu kg per second. After what time will the angular velocity of the disk get reduced to half of its initial value? So this is rotating, and as it rotates, the cotton pad absorbs water, so it gets heavier. As it gets heavier, it finds more and more resistance for rotation. Moment of inertia increases, and moment of inertia in this case depends on the mass added. Mass added depends on the time for which the mass is added. Okay. Now, is there any external torque acting on the system? No. External torque acting on the system is not, it is 0. There is no external torque acting on the system, which means that is the angular momentum conserved? Yes, angular momentum is conserved. Initial angular momentum is equal to final angular momentum. Initial angular momentum is I1 omega 1, final is I2 omega 2. I1 is m0 r square divided by 2, just disk, omega naught. That's right. Now, suppose I consider initial value is omega naught. What is the final moment of inertia? Final moment of inertia becomes, how much is that? m0 r square divided by 2, that is due to the disk, plus the mass added is mu into t, because Mass added is given by mass per unit time into time, mu into t, into r square, because it is on the rim, it is as good as mr square. So this is the moment of inertia, into omega naught divided by 2, because the final angular velocity becomes half of it. So these two cancel and we can simplify it further. So we have m naught r square divided by 2 is equal to m naught r square divided by 2 plus, what is it going to be, mu t into r square, mu t into r square divided by 2. So further simplification is possible. These two cancel. We have m naught square divided by 2 here, and that gives you m naught r square divided by 2 is equal to, what is it going to be? Is it going to be mu t into r square? So t is equal to m naught divided by 2 mu. So these two cancel. So t is equal to m naught divided by 2 mu. So the time after which its angular velocity becomes half is given by this expression, m naught divided by 2 mu. D is our correct choice. Example 5. A wheel initially at rest is rotated with uniform angular acceleration. The wheel rotates through an angle theta 1 in first second and through an additional angle theta 2 in the next 1 second. The ratio of theta 2 to theta 1 is, simple problem. So I can write theta 1, theta is equal to omega naught t plus half alpha t square. So theta 1 is equal to half alpha into t is 1, so 1 square, that is nothing but alpha divided by 2, and theta 1 plus theta 2 is equal to half alpha into 2 whole square, that becomes 2 alpha, that becomes 2 alpha. So now we have theta 1 and theta 2. I can substitute for theta 1 here. So theta 1 is alpha by 2, and that gives you theta 1 is equal to alpha by 2, and therefore theta 2 is equal to 3 alpha by 2, and therefore the ratio theta 2 to theta 1 is equal to 3. Theta 2 divided by theta 1 is equal to 3. Example 5. That is, the answer is theta 1 by theta 2 is obtained as 3. Next one. A uniform rod of mass m and length L lies radially on a disc rotating with angular speed omega in a horizontal plane about its axis. The rod does not slip on the disc and the center of the rod is at a distance r from the center of the disc. Kinetic energy of the rod is. So read carefully. A uniform rod is placed or fixed radially on a disc. It's rotating horizontally, and the rod does not rotate or say slip. So now it's a simple problem. In the case of fixed axis rotation, the kinetic energy is given by half I omega square. It's pure rotational kinetic energy. Half moment of inertia. What is that moment of inertia? Moment of inertia of this rod. So first of all, it is a disc rotating with angular speed, some angular speed. So we have moment of inertia of the disc is mr square by 2 plus moment of inertia of the rod fixed about one end. What is it equal to? So observe that it is going to be moment of inertia Suppose I consider this about one end, it is mr square divided by 12. So if we simplify it, we get it as half m. Kinetic energy becomes, of course, omega square is there, half m omega square into r square plus l square. This is m l square. So let's go outside, l square divided by 12. Next one. A wheel completes 2000 rotations in covering a distance of 9.5 kilometer. The diameter of the wheel is. Distance covered is given. We need to find the diameter and the number of rotations is given. Simple problem. So we can say distance covered is equal to 2 pi r, isn't it? And this can be written as pi into d, diameter, and this is in one rotation. Suppose I consider 2000 rotations, then the distance traveled, total distance traveled is 2000 into pi into d. So 2000 pi into d. What is that d? So if you simplify it, this is you have to find out. Distance traveled is 9.5 kilometer. So d turns out to be 1.5 meter. So the diameter is 1.5 meter. Example 8. The rod OA is rotated about a horizontal axis through O with a constant counterclockwise angular velocity 3 radian per second along this direction. As it passes through the position omega is equal to 0, a small mass is placed upon it at a radial distance 0.5 meter. If the mass is observed to slip at 37 degree, the coefficient of friction between the mass and the rod is, okay. So this is the construction. This is theta and this is mass. It says it is placed at a distance r from this point. This is theta. Starts rotating at a constant angular velocity omega. Now, suppose we consider this one. So, as it is about to slip, it is about to slip, that means it is at the verge of slipping. What are all the forces? I can say this is along this direction, your mg, suppose I consider this, mg is along this direction, and you have mg sin theta along this direction, and mu mg cos theta is along this direction, that's force of friction. And this difference should be provided by the, or this difference should provide the necessary centripetal force. So I can say mg sin theta minus mu mg cos theta is equal to m omega square r. So if I substitute mg sin 37 minus mu mg cos 37 is equal to m omega square r. So m cancels everywhere and you can simplify this one, and upon simplification we get mu is equal to 3 by 16. So 3 by 16 is the coefficient of friction. Example 9. A uniform circular disc placed on a rough horizontal surface has initially a velocity v0 and an angular velocity omega naught as shown in the figure. The disc comes to rest after moving some distance in the direction of motion. Then v0 divided by r omega naught is. v0 is the initial linear velocity, omega naught is the angular velocity. Okay. Now, because it comes to rest, I can say v is equal to u plus at, and that gives me 0 is equal to v0 plus at or minus at, as it is deceleration. That gives me the time after which it comes to rest. Is that correct? Yes. And we can also write omega is equal to omega naught minus alpha t. This gives me again t is equal to omega naught divided by alpha. So I can write v naught is equal to a divided by alpha into omega naught. But what is that linear acceleration? That is mu g. Alpha. Tau is equal to I alpha. So alpha must be equal to tau divided by I. So let us simplify this one. So v naught is equal to, what do we have? Mu g divided by mu mg into r. What is that? Force of friction, and this distance is r. So the torque is equal to F into r. F is nothing but mu mg. Mu mg into r gives me the torque, divided by I. Disc, therefore its moment of inertia is mr square by 2 into omega naught, and this gives me v naught is equal to omega naught r divided by 2, or v naught divided by omega naught r is equal to 1 by 2. So observe what we have done here. We have made use of the fact that it comes to rest and the same time is used to find out the linear and the angular motions. Next one. A cubical block of mass m and edge a slides down a rough inclined plane of inclination theta with a uniform velocity. The torque of the normal force on the block about the center has a magnitude. Okay. Let us consider this arrangement. We can show the construction. Assume this to be theta. Then the block is present here, and what are all the forces? This is your mg cos theta, this is mg sin theta, and normal reaction is along this direction, and it is rough, so friction is also present. This is the direction of friction. Now this distance is a by 2 because it's a cube of side a, so this is a by 2. So now if the block moves with uniform velocity, that's what the data tells us, we must be able to tell F is equal to mg sin theta. Is that correct? Yes, the force up the plane is equal to force down the plane. And now let us consider, see, the question is about the torque of the normal force. So you can say torque of the normal force, if I consider the torque about this particular point, right, the torque due to normal reaction, or say if I consider the about the center of the block, torque due to the normal reaction and the torque due to the force of friction etc. must be considered for equilibrium. That's right? Okay. Suppose I consider the torque due to friction. What is that equal to? That's nothing but force mg sin theta into a by 2. Is that correct? Yes. So this is the torque due to force of friction. Now, as the block is not rotating, as it is in rotational equilibrium, torque due to the force of friction and torque due to the normal reaction must be equal. Torque due to the force of friction and torque due to the normal reaction must be equal, because only then they can produce equilibrium. So I am writing torque due to force of friction and torque due to normal reaction. So torque due to normal reaction is torque due to friction. This is mg sin theta into a by 2. So mg sin theta into a by 2 is the torque due to the normal force about its center. 11. A hoop of radius r weighs m kg. It rolls without sliding along a horizontal floor so that its center of mass has a speed v meter per second. How much work has to be done to stop it? Okay. So there is a hoop which is rotating. It rolls without slipping. It's rolling without slipping along this direction. Now the question is how much work has to be done. So from work energy theorem I can say work done is equal to change in kinetic energy. As the final kinetic energy is 0, I can say this is equal to initial kinetic energy value wise. So what is the initial kinetic energy? Initial kinetic energy is half mv square translational kinetic energy plus rotational kinetic energy half I omega square. Further, half m v square plus half I is equal to mr square. A hoop means a ring. So a ring means entire mass is concentrated only at the circumference. So it's as good as a point mass into v is equal to r omega. So omega is v by r. So I am going to write v square divided by r square. So if you simplify it further, what do we get? This is half m r square by the way. So I get half mv square plus half into this is m half mv square plus half mv square or mv square. So the kinetic energy initially is half mv square. That is the work to be done to stop it. So the work done is equal to mv square. Example 12. A particle is attached to the lower end of a uniform rod which is hinged at its other end as shown. The minimum speed given to the particle so that the rod performs circular motion in a vertical plane will be. Okay. So if I consider is a rod, uniform rod, length of the rod is L and mass of the rod as well as that of the particle is m. This is m, this is also m and its length is L. So now he says the minimum speed to be given so that it performs vertical circular motion. Let us conserve the energy. See, the final system will be something like this. Is here. I am showing a separate diagram. This is present here. This is the initial position, and the final position will be here. This is the final position. So clearly, change in gravitational potential energy is equal to change in kinetic energy. What is that final potential energy? What is that final potential energy? The initial position minus final position. Suppose I take the initial position, center of mass will, where will the final center of mass be located? We can find it out. So center of mass of this arrangement, suppose I take the initial position, I can write mg h2 minus h1. Let's assume that this is at a height h1 from this reference level, and finally it is here. That's right. So by what distance does it rise? Does it rise by a distance of 2 times 3L by 2? Yes. So I have mg into 2 times 3L divided by 2. That is the change in its gravitational potential energy. And this is equal to final energy. Final energy comprises of translational kinetic energy plus rotational kinetic energy. Half mv square plus half I. Moment of inertia of rod plus particle system. How much is that? ml square divided by 3. ml square divided by 3 into v is equal to r omega. So omega is equal to v by r. So I have v square divided by l square. So mg into 2 times 3L by 2 is equal to half mv square plus 2 times mg into 3L divided by 2. And upon simplification, we get v is equal to root of 4.5 g into L. So this is going to be 2 times root of 4.5 into g into L. Okay. So I'll take up some problems based on gravitation. Here is the first one. That is problem number 13. According to this, a planet of mass m revolves in elliptical orbit around the sun so that its maximum and minimum distances from the sun are equal to Ra and Rp respectively. Find the angular momentum of this planet relative to the sun. Okay. So you can show the construction. So maximum distance and minimum distance, Ra and Rb respectively. Angular momentum of this system. Let us see how to do this. Now if I consider the energy conservation, see, notice that here all the answers are in terms of options are in terms of the radii. So if you simplify it, how do we do this? I will consider the energy conservation. For example, at say 2 different positions, at A and at B. So we consider the total energy at A. What do we have? Minus gmm divided by Ra, that is the gravitational potential energy, plus half m Va square. And that must be equal to minus gmm divided by Rb plus half m Vb square. right? And we can consider, because it is a system in which the external torque is 0, we can conserve the angular momentum. So upon simplification, we get angular momentum L is equal to, is actually given by m into Vp into Rp at any point, that is B. So m mass into velocity at B into Rb. So if I use the energy conservation equation which I wrote earlier into this equation and simplify, I get m into root of 2gm R B R A whole divided by R B plus R A. R B plus R A. So this is our expression for the angular momentum of the planet relative to Sun. M into 2g m r p, that is he has taken it as r p here. So r p r a divided by r p plus r a. Next one. A satellite is orbiting just above the surface of a planet of average density d with period t. If g is the universal gravitational constant, the quantity 3 pi divided by g is equal to OK. Now he says the period is t. The period of a planet is given by 2 pi root r cube divided by gm. Let us simplify it further. 2 pi root of r cube divided by g. Mass can be written as volume into density. So we have 4 by 3 pi r cube into d. So if I simplify it further, I have t square is equal to 4 pi square r cube whole divided by g into 4 by 3 pi r cube into d, and that further simplifies to one set of 4 pi cancels and we are left with pi, and 3 goes to the numerator. So we have 3 pi divided by g is there, g into d, or 3 pi divided by, the question is 3 pi divided by g. 3 pi divided by g is nothing but t square into d. So 3 pi divided by g is nothing but t square into d. A is our correct choice. Example 15. A planet revolves around Sun in an elliptical orbit of eccentricity e. If t is the time period of the planet, then the time spent by the planet between the ends of the minor axis close to Sun is. So now we know that aerial velocity is constant. Because aerial velocity is constant, I can write dA divided by dt, that is the area swept per unit time, is constant. Now how to write it? Suppose I consider the time spent in going from one point to another point, that means between two ends of the minor axis. That time t divided by the total time should be equal to the area between those 2 points and the total area. The total area is pi AB. Because the aerial velocity is constant, I can say t divided by t is proportional to, or say equal to, the total time period is, time taken is proportional to its area. So pi AB. And this is the area corresponding to the distance between 2 points corresponding to semi-minor or say minor axis. That is nothing but pi AB divided by 4 minus half into B into EA. That's the area corresponding to the distance travelled between and extremes of minor axis. So T is equal to T into, we can take that pi AB outside. If I take pi AB outside, I will get 1 by 4 minus E divided by 2 pi. So the time required, T is equal to T into 1 by 4 minus E divided by 2 pi, which is our correct option. An artificial satellite revolves around the Earth in circular orbit of radius r with time period of orbit being t. The satellite is made to stop in the orbit which makes it fall onto Earth. Time of fall of the satellite onto Earth is given by, okay. So it's revolving and it is made to stop, and eventually it falls into Earth, and the time of fall of the Earth has to be found out. Now, when it is stopped, the satellite will fall along the radius of the orbit, and it can be regarded as a limiting case of an ellipse whose semi-major axis is r by 2. Let me repeat. When you stop it, the satellite will fall along the radius of the orbit, which can be regarded as a special case or a limiting case of an ellipse with semi-major axis r by 2. Now, according to Kepler's law, we have t square is proportional to r cube. So, time of fall is t dash divided by 2, which is equal to t divided by 2 root 8. Semi-major axis. So you can notice that the this equation reduces to t divided by 2 root 8, or this is 2, or t dash is equal to t into t divided by 2 root 8. So we have this t dash is equal to, if you simplify it further, you get as root 2 divided by 8. This is the time required. So we have t dash is equal to, from this equation, t dash is equal to t into root 2, t into 2. And divided by root 2, that's going to be t into root 2 divided by 8. So the time required is t times root 2 divided by 8. Next one. A homogeneous spherical heavenly body has a uniform and very narrow frictionless duct along the diameter. Let the mass of the body be m and diameter be d. A point mass m moves smoothly inside the duct. Force exerted on this mass when it is at a distance s from the center of the body is, okay. So the construction can be shown like this. This is a duct and this is of radius r, and you drop a mass m, and the question is when it is at a distance s. So let me consider this sphere. The force it exerts is equal to minus, magnitude wise, gm, and if I consider the mass of the shaded part as say some m dash divided by s square. This is the force exerted. So I need the value of m dash here. So to find out it, I will write m divided by 4 by 3 pi, diameter is given. So d by 2 cube should be equal to m dash divided by 4 by 3 into pi into s cube. That gives us the value of m dash. What is that m dash equal to? 4 by 3 and 4 by 3 cancel, and we are left with 1 by 8. So we have m dash is equal to 8 s cube divided by d cube into m. 8 s cube divided by d cube into m. So we can take it into this equation. Therefore, f dash is equal to minus g m 8 s cube divided by d cube into m whole divided by s square, and its value becomes 8 g m m s divided by d cube. So the force exerted on this particle when it is at a distance of s from the center is 8 g m m s divided by d cube. Example 17. Next one. Two concentric shells of different masses m1 and m2 are having a sliding particle of mass m. The forces on the particle at position 1, 2 and 3 are. That means this can be anywhere, maybe at 1 or 2 or 3. It's not sliding about any particular position or say about anything. It can be anywhere. Now the question is, what are all the forces? Okay. So now you can consider it easily that if the particle is here, the gravitational field is 0 and therefore the force is 0. So when the particle is here, the force must be 0. When the particle is at 2, the force is because of the inner sphere. Because at this position, the gravitational field due to the outer sphere is 0. So it is only the inner sphere which exerts the force. However, when it is at 1, both 1 and 2 exert the force. So keeping this in mind, if I consider this is a construction, this is of radius, this is of mass m1, this is of mass m2. So the force at a point inside, that is at 3, is 0. Force at 2 is g m1 divided by r2 square, right, where the distance is r2 square, into mass of this m1 into m. And when it is here completely outside at a distance r1, it is going to be g, both m1 and m2 exert force into m divided by r1 square. So this is 3, this is 2, this is 1 of course. So the forces are g into m1 plus m2 into m divided by r1 square, g into m1 m divided by r2 square, and the force is 0 here. 1, that is here, 2 and 3. So it must be g m1 m2 into m divided by r1 square, g m1 m divided by r2 square, and of course the final force is 0. So D is our correct choice. Next one. Suppose a vertical tunnel is dug along the diameter of the earth assumed to be a sphere of uniform mass having density rho. If a body of mass m is thrown in this tunnel, its acceleration at a distance y from the center is given by. Somewhat similar to what we discussed just now. This is a tunnel and it is at a distance y from the center of the tunnel. Consider a sphere. The force it exerts is g m. This shaded portion is of mass, say m dash divided by y square. So this is g m. M dash is nothing but, what is it going to be? So because it is density is given, I can straight away write 4 by 3 pi y cube into rho divided by y square. But this force is mass into its acceleration. So acceleration is, so you can notice that this m and this m cancel, and one set of y square cancels here. So we are left with g into 4 pi into rho into y divided by 3. 4 by 3 pi y, 4 by 3 pi y g into rho, or it's directly proportional to y. So acceleration is directly proportional to y, and of course that acceleration is oppositely directed. As you can notice, it is an a pulling force. So 4 by 3 pi g rho y. Three particles p, q and r are placed as per the given figure. Masses of p, q and r are root 3m and m respectively. So p is here, q is here and r is here. Masses are root 3m and m respectively. The gravitational force on a fourth particle placed at a distance root 3d is equal to, okay. So let us see what is the direction of this force and the magnitude of the force as well. So the construction is like this. This is root 3m and this is root 3m, this is p, this is q, this is r, and this is 3d, and this is root 3d, and this is of mass m, and of course this is root 3m and this is m. Now what are all the forces on m? The forces are, number 1 this force, number 2 this force, and number 3 this force, and this distance is d, of course. So now if we write the forces on this particle, let's see what are all the forces on the particle. Now this is F1 I call, and this is F2 and this is F3. What is this angle and what are this angle? So you can notice that this angle is nothing but, this is root 3 and this is 3, and clearly what is this angle? This angle theta is equal to, or say I can write tan theta 3, that is 1 by root 3. So what is that? Is it 30 degree? And this is 60 degree clearly. So F1 cos 30 minus F2 cos 60 is equal to 0. What is that? If I simplify it further, this becomes g root 3 m into m, this is of mass m, divided by, what is this distance? This is 9 plus 3, 12. So this is nothing but root 12. This distance is root 12d. So 12d square into cos 30. That must be equal to F2. The force between this and this, I'll consider it as F3. F3, what is that F3? F3 g m square divided by, this is root 3, so 3 plus 1 4, so clearly this is nothing but 2d. So 4d square into cos 60. They may not be equal to each other, so I will write fx is equal to this minus this, so fx is equal to this minus this. And are they equal? We'll cross check it. So are they? So this is root 3 divided by 12 cos 30. If you simplify it, what do we get? G m square divided by, this is 12. I can write it as 4 into root 3. Correct? Cos 30 is 1 by 2. This is equal to, or this minus, G m square divided by cos 60 is root 3 divided by 2. So I am going to get it as, once again, 4 root 3 1 by 2. So this turns out to be 0. So we have this fx. Likewise, similarly, we have fy. What is that fy? Root 3 g m square divided by 12d square cos 60 plus root 3 g m square divided by 3d square plus g m square divided by 4d square into cos 30. This is the contribution from f1, contribution from f2, that is f1 60 cos 60, and then we have f3 cos 30. So we can find out the value of fy. And the net force turns out to be root of fx square plus fy square. And as fx has turned out to be 0, clearly the force is along this direction. That means along which direction? This is along the direction s to q, s to q. And you can simplify it to get the magnitude as root 3 into g into m square divided by 2d square. So root 3 gm square by 2d square. Root 3 gm square divided by 2d square along SQ. This is the direction of the force, and that is the net force, and the direction is of course along SQ. So C is our correct choice. So with that problem, we have come to the end of this discussion. So please go through these problems one more time, familiarize yourself with these equations, with these concepts. Thank you very much.